Welcome back. So we'll continue now with white column stores. Who was scared by XML and JSON? Who was scared? Who finds it easy? Okay, very good. I like that. Okay, so now let's move on in our technology stack, because we already did pretty much all of that. And now we continue to move up. So now we'll go into data modeling. This and next week, actually, we'll look at data models, and then we'll continue to work our way up the stack, right? Everything just fits together. In fact, I'd like to go back to tables. We've rehearsed tables in the brush up of SQL for relational tables. But the thing is, PostgreSQL, so what we've been using, it's installed on a single machine. You have a single machine, all the data is in there, and everything works on the CPU of the machine, right? So now, in the 2000s, something happened with many companies, especially the large corporations, that started having so much data that it didn't fit on the same machine, but they still wanted their data to be like tables, right? So how do you deal with this? So you could scale up and buy bigger machines with more memory, more space, more cores, and so on, but there are limits. If you want to download the entire internet, that doesn't work, right? You will not find a machine that stores it all, right? So the first idea, and that was actually done in the companies in the very early 2000s, I would say, the engineers started hacking a few things around. So they said, okay, let's install some relational database management system on multiple machines. Let's buy 10 computers. On each one of these 10 computers, we will install PostgreSQL, for example, and then we'll store tables but spread over the machines. It's, for example, instead of having a table of people all stored on the same machine, you're going to have to cut it in 10 partitions. You're going to have 10 tables of people, one on each machine. And on every machine, you have 1/10 of the people, right? It's called sharded across machines, just like the blocks in HDFS. And you might even replicate, right? You might have 5 machines and then again 5 machines. So you split it in 5 on the first 5 machines. Then you have copies again on the next 5 machines. But of course, it's a hack, right? Because when you do that, you need to remember what machine has what and what is replicated where and so on. It's very costly. It's very costly, and it quickly goes into development costs, maintenance costs in order to make this all work. So at some point, it started hitting the limits in terms of engineering costs, right? So it's very hard to set up, and you cannot do that forever. However, doing that gave first ideas. For example, the idea of sharding, the idea of replicating, that actually already started appearing there. However, we've looked at HDFS, also Amazon S3, Azure Blob Storage. So we have already a way to store data across 10,000 machines. We already know how to do that, right? But we do it with files. I can store a hierarchy of files organized in directories on 10,000 machines, petabytes of that, right? This is what we saw last week and the week before. But it's files and directories. And as I told you, that's what we were doing in the 60s, files and directories. And then we replaced all of that with data independence and tables. So what we want to do here is kind of the same thing. Can we do, just like in the 70s, we built on top of the file hierarchy on the single machine, a relational database management system? Can we do the same thing right here, but this time on top of a distributed file system, right, with files? And the answer is yes. And the technology, the sort of technologies that do that is called a white column store, right? There are several of them. We are going to be looking into HBase, which is the open source version of Bigtable. That's how Google called theirs. There's also Cassandra that was used by Facebook, now Meta. So there's multiple implementations. So we'll focus on HBase, but keep it generic enough that you will understand how this actually all works, right? So the idea is that HBase is running on top of HDFS, right? So this is in fact, the H is the same, right? The H is in HDFS is Hadoop, and the H in HBase is also Hadoop, right? All right, so far so good. So this is the idea. We're going to implement something relationally on HDFS. All right, now, why don't we use existing systems? And I tried to have this kind of compilations of pros and cons on what we've seen so far. we have the object stores. So for example, the S3, Azure Blob Storage. We have the good old relational database management systems. We have HDFS in itself, a file system. We have key value stores. If you have these requirements here, high throughput, low latency, support for updates, large values are supported, large collections, random access, none of them actually checks all of the boxes. So that's the current limitation. Yes?
Can you explain why HDFS has low latency or has high latency?
High latency? It's the idea that whenever you enter a comment in POSIX-like, remember this Hadoop FS or HDFS DFS, every time you click enter, you press enter, it's going to take 1 or 2 seconds. And that's considered a high latency, you know, whenever you access it. So this is a limitation. We want something better than that.
Isn't the block size chosen so that the latency is as small?
It's not just the block size, it's the fact that you go over the network and you are reading it from the disk. It has to do with this, the idea, right? So this basically shows latency. And now maybe you're going to be asking, how can it be that we have HDFS that has high latency in relative terms, and we managed to implement on top of HDFS something that has low latency, right? That sounds like magic. Well, I will show you how, because actually people managed to do exactly that, something that has much better latency than HDFS. All right? So this is the cliffhanger for HBase, but you will understand when I explain to you the internal design, right? So I will not comment further. There's just all of these points that we would like to achieve, but none of the systems actually achieves that, and this is why we have these white column stores, right? It checks all of the boxes right there. So I just have to warn you, it's a complex piece of technology. I'll take the time to go through it. I'll answer your questions, and we will see that there is a lot of very valuable lessons to learn from the architecture of HBase. And a lot of these lessons will even apply when we look into MapReduce, Spark. So there are patterns, big data patterns that you will start recognizing, right? So be prepared for a slightly more complex lecture, but we will manage. Okay? Who is ready? Okay. So probably not finished today or tomorrow, but we'll just take the time. Okay, so now I told you that I like, when I introduce a new system, to first talk about the logical layer, and then I talk about the physical layer, right? This is what I did with HDFS, right? I first told you in HDFS, we have a hierarchy of files and directories. The files are organized in blocks, and that's it. That's the data model. And then I went into the physical architecture with the name nodes, the data nodes, and so on. I'm going to be doing the exact same thing here. I'm going to start talking about the logical model of HBase, the white column store, but without giving you any details on how this is all implemented. We'll take care of that later. So I start with the logical model. So again, I have slides about that. It originated at Google as Bigtable. Who heard of Bigtable? Okay, a lot of you, right? There's also BigQuery that is also quite known, right? So BigQuery is to the kind of on the query side. All right, but HBase is pretty close to Bigtable. Just to give you an intuition, it also has to do with denormalization in a way that is also linked to the way we denormalize to XML and JSON. But even if you don't go below the first normal form, like let's just go down from the third or second normal form to the first normal form, it's the idea that if we have multiple tables, we are going to have to do joins, right? So it means, for example, that's a table on the left, a table on the right, and there are foreign keys and primary keys that are linked, shown with the arrows. Joining is actually expensive. We would like to avoid that. In particular, we would like to avoid that because the data is spread all over the cluster. It's spread over 10,000 of machines. Imagine the mess this is going to be if we need to join all the time. Every time somebody queries the system, we need to join across an entire cluster. We'll see it's possible in a few weeks, but ideally, we would like to not do that too much. What is the solution to that? Well, probably no denormalization, right? So it's the idea of storing together what is accessed together. So we denormalize the whole thing, and what we get is, for example, I take these two tables, and if the clicker works, that's what I get. Right now, I just put them in one table. It's basically the idea of multiple tables merged into a single table. You will introduce duplication. You might have data repeated multiple times, but this is just something we are fine with, right? So we try to take that, squeeze it into a single table like this, and this is it. And now you see the duplicates, some duplicates appear, right? But this is fine. So this is one of the things we're doing with wide column stores. In fact, that's why it's called wide, right? So it's going to have more columns. But there's another reason it's called wide, is that it's going to be very sparse, is another reason. Okay, so in a typical relational database management system, even though now it probably evolved, but back then the number of columns in a table was limited to 255 or 256, right? Anything beyond that would break. In a wide column store, we can have millions of columns, right? So this is one major breakthrough compared to a classical single machine relational database. All right, so the logical model. First, one of the columns is special. It's the row ID. It's the primary key. The row ID uniquely identifies the record. If I tell you 22A, you know that I'm talking about this record right there, right? So it's a primary key, technically, but always exactly one column. One column. It's never multiple columns like you could have in a relational database. Always exactly one column. Cassandra allows multiple columns, but Bigtable and HBase is just one column. All right, that's the row ID, and it's sorted, right? I sort by row ID. Technically, these are just bytes, right? The row ID. All right, so I sort like this. So since these are bytes, you know, we like to use base 16 in order to represent bytes. Okay, so it's kind of a key value model, right? The key would be the row ID, and the value is the rest of the records. Who sees the key value model in here? Right? It's kind of an extension of the key value model. It's just that now the value has columns. That's the difference. All right. Second, that is another difference with the relational database management system. We have column families. It's not just that we have columns, we also have an additional hierarchy of columns where we have the column families and then the columns, right? So I use colors in there. There is a purple column family, the yellow column family, the red column family. The reason we have them is that typically when we access the data, we are going to access only one family at a time or two families, but not all of them, right? And just to give you an intuition, when we denormalized the data, typically the different column families would correspond to potentially different tables, right? But when we bring them all together, we just have these column families, right? So these are the groups of columns that would come from all the different tables. That's just an intuition, high-level intuition. All right, so we have these column families. In other words, if you want to uniquely identify a columns, you need the column family plus the name of the column within that family, right? So I used the Latin alphabet for the purple family. I use the Indo-Arabic numerals for the yellow family and the Roman numerals for the red family, all right? Just to give an example. So if I say purple A, or purple B, or yellow 2, or and so on, that uniquely identifies the column. But I need both the column family and the name of the column. So far, so good? So now, if I want to identify a cell, I need the row ID, the column family, the column name. If I tell you, for example, 0A1 purple B, I'm here, right? The row ID is 0A1, and I'm in purple column family, column B, right? This is the data model, right? Now, something important is that unlike in a relational database management system, you can create columns on the fly. You can make up new column names when you insert new records, just invent new columns, that's totally fine. In a relational database management system, it's not so easy. You need to do this alter table, add column, blah, blah, blah. And it's not going to happen instantly. You have to wait until it actually does that. But in HBase, it's magic. You can just create a new record that has more columns, new columns, and it's totally fine. It's instant. You don't have to wait for that. But I said columns, not column families. Adding column families takes a bit more time. So adding new column families shouldn't be done too often, but adding new column names is totally fine. And this is why, in the end, you're going to have relatively sparse tables in there, right? So you can have 1 billion rows and 1 million columns, But of course, you are not going to have one cell for every combination, right? Because otherwise you would be talking about quadrillions of cells, right? So it's going to be very sparse. Okay, so that's the intuition. All right, so you can add here, for example, I added some columns on the fly, maybe because of a new record. It's empty in a lot of places, of course, but you can really do that without any problems, right? Okay. So far, so good? All right, now another difference with the relational database management system. If you use PostgreSQL, you know that the columns have types. You can have varchar, integers, dates. Who saw that, right? Who remembers that, right? You have these very nice data types in a relational database system. In HBase, that doesn't exist. You don't have types. The reason is everything is bytes, everything, literally everything. So what you have is there is a sequence of bytes, the column name is a sequence of bytes, the row ID is a sequence of bytes, and so on and so on. We don't even have any types. So what happens? Does it mean we cannot use types? Yes, of course we can use types, but it's your problem as a user to deal with that. HBase doesn't care about types. So you can have, of course, in the libraries in Java and in other languages, you can have some nice functions that kind of add some convenience layer to handle types, but HBase doesn't care. Everything is just a sequence of bytes. Does that make sense? Right? So it's slightly on a lower level than a relational database management system. But this is an intuition I gave you earlier. If you want to scale up and go to larger scales, you have to simplify things a little bit to make it more manageable. And this is an example. Everything is a byte that simplifies things. All right. So everything is a binary. Something else to continue to give you the intuition of the sort of things that you are going to put in there. You can put small values, of course. You can put, just like in a relational database management system, a small string, an integer, and so on. That's totally fine. But you can also put in one cell, and really just the same cell, typically up to 10 megabytes of data. And that's totally fine. It's within what HBase does well. Up to 10 megabytes in every cell. I'm not saying you cannot do more, but if you do more, you're pushing the system to the limits, and maybe it's going to work less well. But up to 10 megabytes is the intuition. Now, what do you think are we going to put in the cells when it's 10 megabytes? Yes? Yes, what kind of files? Yes, that's exactly, yeah. So you're completely correct. Images and so on, and XML and JSON. So it's not uncommon to put in the cells XML, JSON, and so on. So you see why it's worth learning it, right? It's everywhere. And indeed, you will find very often some XML and JSON stored right there in the cells of HBase or Bigtable. I told you these are bytes, right? And it's bytes, so you can store an XML document or a JSON document as bytes, right? But images and anything else is totally fine too, right? So this is the intuition. Now you see that this is something that goes a bit beyond, for example, a key value store. We saw a key value store is typically a few hundreds of kilobytes, right? So this pushes a bit further. And a relational table technically could also, now the modern ones can also handle that sort of thing. But the ideal use case, you don't do this in a relational database, right? But in HBase, it's totally friendly with having big cells like that. You could even have HTML in there, right? If you have a blog or indexing the web, you can store the web pages in there, right, in the cells. Okay. So this is what we have there, and that's the logical level. So first, that's the data model of what we have, right? So we have tables that have a row ID, column families. Then you have columns. You can add columns on the fly. You can have millions of them. But columns families is not something on the fly. That takes a bit more time to add a column family. And we can store up to typically 10 megabytes of data in one cell that can be XML, JSON, pictures, and so on. Now let's move on to the sort of queries we can do. So this is also a bit lower level than a relational database management system, because in PostgreSQL, you have the SQL language that allows you to, on a high level, select, project, and so on. Here, we have a bit less than that. It's a lower level. We can do 4 things: get, put, delete, scan. So let me quickly explain. It's closer to a key value store in that sense. First, I can get some data. If I give you a row ID, I can retrieve all of the values in all the columns associated with that row ID. I can also say, only give me the purple and the yellow column families, right? So you can also only pick some of them. But this is a get operation, right? Then we have the, do I have a question? No? Then we have the put operation, which is please insert this new records with this row ID, and then you can supply values for some columns. Don't have to be all of them. It doesn't even have to be all column families. You can say just put 2 or 3 columns in there, even though there's 10,000 columns already. So it's very sparse, right? But you can add records like that. It's a put, right? Again, it's a bit more complex than the key value store, because the key value store, you just put a value and that's it. Here you put multiple values because you have these multiple columns. So get, put. Then we have, yes?
You always insert at a row ID, or can you just say insert this?
I think you need to specify the row ID when you insert.
So you have a pre-populated list of potential row IDs.
It's just sequences of bytes.
Okay.
Right. In fact, so I didn't say what the row IDs are, but typically, if you use HBase as a user, you will decide what your row ID is. For example, if you're storing people, you might take the social security number as the row ID, right? And you put it as a sequence of bytes. So typically, even though the row ID is a sequence of bytes, in general, you will have an idea of what you put in there. It can also be something that is a compound thing, right? Imagine that you have a compound key. You just merge that into a sequence of bytes that has anything that identifies the records. But this is really for every use case, it's going to be something different, right? Now, it sounds trivial. It's not, because if you're not careful, you might create what is called the hotspot, in the sense that you will have a concentration of row IDs that are within certain intervals and not in others, and that can create problems, right? So we'll come back to in the architecture how that works, right? But the design of the row IDs is part of the user's job, right? Yes?
So can a row ID be 10 megabytes too?
Sorry, I didn't
Row
understand.
ID, can it be 10 megabytes?
Oh, that's a good question that I didn't check. I think it could, but I'm not entirely sure. Let's write that down also for something that we'll check offline, right? It's not technically that you could not, it's really the idea of, is it something that would kind of make it slower to a point that it's unusable, right? So it's really about how people use it, right? Yes? Exactly, yeah. So exactly, you have to basically ask yourself, do I really need that, right? Yeah, so that's one way of looking at it, right? That maybe you don't need that because you can always find a shorter way of identifying. You could, for example, if you have something 10 megabytes, you could take the hash of that as a row ID. But it doesn't remove the question that if we want, can we? And so we can still try to look that up, right? Okay. All right. So let's move on to the, oh, we have another on Zoom. Small hops. Yeah. Yeah.
What is the significance of adding the column families relative to the normal columns? Like maybe I missed it, but I didn't quite get it.
It makes the system faster when you want to partially read the data. The idea is that if you are only interested in reading the purple columns, the fact that you have separate column families, we will see that it's also something that is physically reflected in the storage, and it will make it very efficient at quickly retrieving just the purple column family, right? So if you have several column families, that helps you. It's called projecting away the data, right? It's the sort of optimizations that can be done in a system, right?
Okay. Thank you.
Yes, over there, we have questions. Oh la la. We need to give the feedback because they leave it permanently here, but we should give them the feedback that it's
so you noted before that we could group data based on data which we would need to read together with other data. Is this what these
Yeah.
families are?
I'll get to that on
and-
the physical level.
Okay, then can we have overlapping families, columns?
No, they don't overlap.
Okay,
it's separated.
and in that case, I mean, how do we predict that certain data would be read together with
Oh.
certain other data? It's rather
So the
complicated
intuition
issue.
would be semantic. It's like, what are you storing? For example, I don't know, imagine that you're storing a blog. So you might have that part that contains the HTML of the blog. Maybe that part is about the access control and who can modify it and so on, right? So the idea is that the column families correspond to some meaningful thing that you need. So it's really about what do you need to access at the same time, right? So you will, if there are regular patterns that very often you just need this or you just need this, then it means it's a good design to have separate column families, right?
And is there a way to adjust this on the fly? I mean, if we figure out that there's a certain use case where certain data gets read, we adjust those families.
You can change them. It's just that it's going to block the system for a while you are doing that or slow it down, right? So it's not that you cannot create column families or change, but you might need to wait until this is done. So it takes much more time to modify the column families than it takes to add or remove columns, right?
But it can be dynamic.
Technically, it can be dynamic, but it's dynamic in quotes, in the sense that it might, it's like building an index in a relational database, right? You can do it, but maybe it takes 3 hours until it's done.
Thank you.
Yeah, thank you. On Zoom, I think there was also somebody.
If we always need to specify an existing row ID when inserting a new row, then do we ever actually insert an entirely new row with a new row ID?
Yes, because you need to distinguish. So you only have the row IDs that you have inserted so far, right? You only have those that already exist. There's also all of those that do not yet exist, right? So you can just add at any time one that doesn't exist. Does that make sense? So it's not like you have all of your row IDs pre-populated with empty values. It's nothing like that, right? Yeah, awesome, perfect. So get put, the next one is scan, right? Scan starts being big data. What if you want to go through a very large portion of the table and just scan through it? You might be looking for something, you might be aggregating, you want to iterate. So there is this scan. And the idea is that it gives you a way in the programming language, in the host language, to iterate through all of these rows, right? Here I marked everything, but you can also scan only the purple column family or only the yellow column family, so you can restrict. And on top of that, you can also scan, so here just a column family, you can also scan a specific interval of row IDs, right? I told you it's sorted, so you can say there's an upper bound and a lower bound, and you only scan in that specific interval and for that specific column family, right? So this is the sort of things that you can do. And finally, delete. Say you can delete some values or even an entire row with the row ID. So get, put, scan, delete, and that's it. So it's very low level. It's nothing like the high level SQL and so on. There are people who implemented SQL on top of that. There's Hive, there's systems that do that, but HBase itself just sticks to get, put, scan, delete, right? For whom is that clear? And you can interact with that via the shell or via Java or a language. Yeah.
Does delete actually delete that row or the selected rows, or does it disable them whenever you're trying to scan the array afterwards?
That's a physical detail. Very good question. So the idea is when you delete, do you really, really delete? Or do you just mark as deleted, right? That's the question. Well, the answer is that it's only marking as deleted. But this is a physical detail, because on the logical level, at least if I don't care about versions, I don't see that, right? However, and maybe that's a good opportunity for me to add that to the logical level, there is some sort of versioning possible with HBase. Is that when you modify, it keeps track of versions. If you override a value in a cell, creating a new version with a timestamp, and when you delete, it still keeps the older versions, but if you request the latest one, it will not see it. If you travel back in time to an earlier timestamp, then it will see it, right? And the timestamps are even exposed to you. So you can even say, this is the timestamp I want to store, right? So it doesn't have to be just the latest. All right, does that make sense? And I'll come back to that on the physical level, right? But it's true that it could be considered part of the logical level that you have some versioning capability in HBase, right? It remembers the past. Okay? Yes?
Is it possible to make also operation based on the column names? Like, for example, deleting a column or like put yeah, basically like delete an entire column without specifying the row ID?
It might be possible that we can check too. I'm not entirely sure. We'll check that too. Yeah, that's a good question. Yeah. Yes, over there. I think I'm trying to actively think how we can do this. Maybe a better way is to just bring it. Like we can just take the microphone and I mean, we can do it, or we need to find a way that works in the long term, because this just throwing it and scaring people, I don't think that we can do that forever. Go ahead.
Can we just put all columns into one column family? Because you said it's fast to create a new column, but long to create a new column family. So we can just put all together and then we are
technically,
fast.
yes, you could. But again, if you start having a lot of data, at some point you might see a performance drop. And if you often have to access only some columns and not others, this is where you start getting a benefit of splitting into multiple column families, right? But it's really use case dependent. But technically, yes, you could put everything in the same column family, right?
Top. Thank you.
Okay. Thank you. Maybe there's some documentation we can look up that they tell us how it's supposed to be thrown. All right. So, all right, now a bit of terminology. I often talked about the key value model, but the key value model is a logical thing, right? We have it in the key value store. We have it in HDFS, the idea that every file is associated with a list of blocks. We have it a little bit everywhere, but the key value model is only whenever you see a map, abstract data types. So you could see some key value model in HBase in the sense that the row ID is the key and all of the other values in the columns are the value, right? Not to be confused with key value store, that is specifically the technology like Dynamo that implements it, right? Then there is the notion of column stores or column storage. It's not the same thing as the white column stores we're talking about. Column stores, we are still talking about relational databases, but usually, at least in the old relational databases, the way it's stored on disk is row by row. So you store an entire row of a relational table together on the disk. So you have a row, then a row, then a row, then a row. Column storage was introduced a bit later. It doesn't change the logical model. You still have a table, but the way it's stored on disk is column by column, right? And the benefit you get out of that is similar to what we have with column families. It means that if somebody is only interested in column 1, then it's going to be much faster to read the data because it's all together on the disk. If you store it in a row fashion and you're only interested in column 1, you have to read much more from the disk, and then you just filter out what you don't need. So that gives you, the column storage gives you a benefit in terms of disk I/O, right? And the white column stores, it's kind of an extension of that with the idea of column families, right, that are stored together. And again, what you want to do, remember that the bottleneck of big data is the disk I/O, right? The fact that we have huge capacity of storage, but we cannot read fast enough. So whenever we can avoid reading something, then we should avoid reading it. The column families help us doing that, because if you know you only need the purple one, then you're only going to ever read what's in the purple column, and you're not even reading what's in the yellow one, right? So this is the idea, right? And you'll understand also when I come to the physical storage, it will make sense, right? Let's bring it to, yeah.
So if the columns store all the rows, the data in the row, wouldn't it slow down if you have a lot of rows?
The column store?
Yeah.
Yeah. So it's always based on the use case of what you want to be doing, right? There are also technologies that have a hybrid approach to a bit row-wise, a bit column-wise, and then they do some sort of you know, horizontal and vertical partitioning of the way that it's stored, right? But we are not talking about column stores in this course. This is just, you know, to make the distinction, right? So this is the column stores, but now this is what we are talking about, the column families. All right? Yeah. Any other questions? No? All right. Let me. Thank you. There you go. Okay. So these are the column stores. Now, just so you know, there's Bigtable, there's HBase, there's Cassandra, there's plenty of them. If I teach you HBase, you will have no difficulty learning any other one. You just need to look up the documentation. There's going to be small details that are a difference, but the principles are really the same, right? Okay. Now, if we go to the physical level, I will not tell you much, but just this last thing before we leave. How do we store that physically? I could have billions of rows and millions of columns. So I need to partition. For the files, it's easy. A file is a sequence of bytes. So we just cut every 128 megabytes, we cut and we have the blocks. But here it's two-dimensional, not just the one dimension. So what do we do? What do we do? It's like a wedding cake. You just cut it horizontally and vertically. So it means that first we partition it horizontally in intervals of row IDs. So I always give you the first row ID included and the last row ID excluded. It's just so that it's also the beginning of the new one, right? So I give you an interval of row ID and we partition the table like this. Every one of these layers and intervals of row IDs is called a region, right? A region is a partition of the row ID space. And additionally, we also partition vertically. So it means that what we store together on disk, and that we'll show you tomorrow, is for a specific region and the specific column family, the intersection of the two, that's what we call the store, right? We store it together. So you see, it's really like cutting the cake horizontally and vertically. This is how we cut the table. And every intersection of a region and a column family gives you what is stored together. And you want to keep the size here reasonable so that it's practicable and gives you performance. So I'm going to stop here because we have just 2 minutes left. And tomorrow I'll continue. There's going to be a few things that we'll find very familiar, but I leave that as a cliffhanger. So thank you very much. And I'll see you tomorrow at 9 a.m. in the auditorium over there.